Hi, welcome to iEducator. This is Teacher Jeff. I'm an educator and an engineer by profession. And today we will discuss Chapter 3. And Chapter 3 is all about linear programming models, solution by Simplex Method. And in this lesson, there are 5 key areas that I'm going to be highlighting today. First is the introduction to Simplex Method. Second, comparison between graphical and Simplex methods. Third, terminologies used in solving linear programming problem using Simplex Method. Fourth, the maximization problem. And lastly, we have the minimization problem. Now, as discussed in the previous chapter, there are many methods to solve the linear programming problem, such as the graphical method, the trial and error method, the vector method, and the simplex method. Though we use graphical method for solution when we have 2 problem variables, the other method can be used when there are more than 2 decision variables in the problem. Among all the methods, simplex method is the most powerful method. So what is meant by simplex method? If we say simplex method, it deals with iterative process, which consists of first designing a basic feasible solution or a program and proceed towards the optimal solution and testing each feasible solution for optimality to know whether the solution on hand is optimal or not. In other words, if the solution is not optimal, then we need to redesign the program and test for optimality until the test confirms optimality. Therefore, we can say that simplex method depends on 2 concepts, known as first, feasibility, and second, we have optimality. Simplex method is also defined as based on the property that the optimal solution to a linear programming problem, if it exists, can always be found in one of the basic feasible solutions. Now, this means that the simplex method is actually quite simple and mechanical in nature. The iterative steps of the simplex method are repeated until a finite optimal solution, if exists, is found. If no optimal solution, then the method indicates that no finite solution exists. And the second key area that I'm going to be discussing right now, that would be the comparison between graphical and simplex methods. So what's the difference between the two then? First, the graphical method is used when we have 2 decision variables, whereas in simplex method, the problem may have any number of decision variables. Again, in graphical method, we only need to deal with 2 decision variables. On the other hand, for simplex method, we are dealing about more than 2 decision variables. Now, the second difference between the two is that in graphical method, the inequalities are assumed to be equations so as to enable to draw straight lines. But in simplex method, the inequalities are converted into equations by adding a slack variable in maximization problem and subtracting a surplus variable in case of the minimization problem. Now, if we say slack variables, these are the variables added to constraints to convert them into equation. On the other hand, if we say surplus variables, these are variables subtracted from constraints to convert them into equation. And the third comparison between graphical and simplex method, that would be in graphical solution, the isoprofit line moves away from the origin towards the far off point in maximization problem and in minimization problem. The isocost lines move from far off distance towards origin to reach the nearest point to origin. Now, if we say isoprofit lines, these are lines composed of amounts of labor and its total output that yield the same amount of profit for the firm. And on the other hand, if we see isocost line, it is a graphical representation of various combinations of two factors, which is the labor and the capital, which the firm can afford or purchase with a given amount of money or total outlay. It is an important tool for determining what combination of factor inputs the firm will choose for production processes. And the fourth comparison between the graphical and simplex method, that would be in graphical method, the areas outside the feasible area, which refers to the area covered by all the lines of constraints in the problem, indicates idle capacity of resource, whereas in simplex method, the presence of slack variable indicates the idle capacity of the resources. And finally, the last comparison between the graphical and simplex method, in graphical solution, if the isoprofit line coincides with more than one point of the feasible polygon, then the problem has second alternate solution. In case of simplex method, the net evaluation row has 0 for non-basis variable. The problem has alternate solution. Okay, and the next key area that I'm going to be highlighting right now, that would be the different terminologies that are commonly used in solving linear programming problem using the simplex method. So these are the common terminologies that we usually encounter, especially in solving linear programming problems using the simplex method. First, we have the standard form. Now, standard form is the way of expressing the constraints of a linear programming problem as equalities, with all on the left side of the equation and a constant on the right side. Second, we have slack variables. And as mentioned earlier, when we say slack variables, these are variables added to constraints to convert them into equations. Another term that we usually use in solving linear programming problems, applying simplex method, that would be surplus variables. And as discussed earlier as well, if we say surplus variables, these are variables subtracted from constraints to convert them into equation. And another, we have artificial variable. And if we say artificial variable, it is a computational device used in linear programming to achieve an initial solution to the problem. Next, we also have what we call iteration. And if we say iteration, it is a simplex method which consists of the sequence of steps or row operations performed in moving one basic feasible solution to another. Next, we have simplex tableau, or this is a table used to keep track of the calculation made with the simplex method employed. And another, we have what we call quantity or constant column. When we say quantity or constant column, this is the column in the simplex tableau, indicates the quantities of the variables in the solution. Another, we have basic variables. And if we say basic variables, these are the variables included in our basic solution. And also we have optimum column. And optimum column is the column in any solution to a maximization problem which has the largest positive value in a maximization problem. And next we have intersectional elements. And if we say intersectional elements, these refer to elements common to both optimum column and the rows representing variables in the solution. And next we have pivoting. And if we say pivoting, this is the process of going from one simplex tableau or table to the next tableau or table. And next we have pivot row. What is meant by pivot row? It is a row in the simplex tableau or table corresponding to the basic variables that will leave the solution. And finally, we have pivot. And pivot is the element of the simplex tableau or table that is both the pivot row and the optimum column. Now, these are the basic terminologies that we commonly use or encounter if we are trying to solve linear programming problems applying simplex method. Now, I totally understand that you still have confusion because these basic terminologies can only be best understood by providing specific examples. So later on, we will be providing examples under maximization problem and minimization problem in such a way that these basic terminologies will be meaningful. Okay, so we also have rules for preparing constraints in simplex method. So how do we prepare constraints if we solve linear programming problem using simplex method? Now, as you can see in the tabulation, we have three different constraints. We have less than or equal to, we have equal, and we also have greater than or equal to. And in the next column, we also have adjustments. And the last column is our objective function coefficient. Divided into two, we have the maximization and minimization problem. Now, for the less than or equal to constraint, now supposing our objective function or our linear structural constraints or non-negativity constraints are having constraint of less than or equal to, then the adjustments that we are going to be needing to do is to add a slack variable. Now, based on the objective function coefficient, if our problem is a maximization and minimization problem, then we can apply O, okay? Next, we have equal constraint. Now, what if we are seeing equal constraint in our objective function or both the linear structural constraints and non-negativity constraint? Now, if it's equal constraint, the adjustment would be to add an artificial variable. And based on objective function coefficient, if it's a maximization problem, we need to make use of negative m. And for minimization, that would be positive m. And lastly, for the greater than or equal to constraint, we need to subtract a surplus variable and add an artificial variable. If we subtract a surplus variable for maximization and minimization, that's positive O. And if we add an artificial variable, that's going to be a negative m for maximization and a positive m for minimization. And the next key area that I'm going to be discussing right now, that would be the maximization problem. So before going into an example, I'm going to be discussing first the different steps that we should follow in order to solve a maximization problem. Now, there are a couple steps in solving a maximization problem. Now, the first step is to, of course, we need to set up the constraints from the condition of the problem, because normally we will be given a worded problem. And based on the worded problem, or word problem rather, we're going to be needing to construct our objective function and also the two different constraints, which are the linear structural and the non-negativity. And remember, we need to set up those constraints based on the word problem, how we understood the problem. Second, after setting up the constraints, the next thing that we need to do is to convert the inequality linear structural constraints to equation by adding a slack variable. Okay, so in order to do that, we need to add a slack variable and then convert this into an equation. And the next thing that we need to do is to enter the numerical coefficients and variable in the simplex table. And fourth, we need to calculate the C sub j minus Z sub j values. And in getting the value of Z sub j, then we need to follow the formula shown. Okay, so that will be the formula that we're gonna be employing if we calculate the value of our Z sub j. And the next step, that would be to determine the optimum column, or entering variable choosing the most positive entry in the C sub j minus Z sub j row. And we need to divide the quantity or constant column by the non-zero or non-negative entries in the optimum column. The smallest ratio will be our pivot row. Next, we need to calculate or compute the values of the replacing row by dividing the entries of the pivot. And take note, our formula in getting the replacing row, that would be a pivot row divided by our pivot. And next, we need to compute the new values for the remaining rows using the following formula. So in getting the remaining row value, that would be the old row minus the intersectional element multiplied by the replacing row. The other formula that we can employ or use in getting the new value, that would be the old value minus the corresponding key column value multiplied by corresponding key row value all over our key element. And the last step in solving a maximization problem, to calculate Z sub j and C sub j minus Z sub j values, we need to enter the results in the tableau 2 or table number 2. In the C sub j minus Z sub j row still contains a positive entry to the step identifying the pivot row. Then we need to calculate the values of the replacing row by dividing all entries by the pivot. And after, we need to compute the new values for the remaining row using the formula shown in step number 6. And then we need to enter all values in the tableau 3. Now, I totally understand again that this is quite difficult to understand as of yet. It's because we have not provided any examples yet. And so for this matter, don't you worry, because later on, we will be providing specific examples and we need to apply these steps in solving a maximization problem. And before that, let me discuss to you first the steps in solving minimization problems. So if we have a step-by-step process or procedure in solving a maximization problem, then that is also the same or uniform, or that's in sync with the minimization problem. Now there are also a couple steps that we need to follow in order to solve a minimization problem. The first step that we need to do is, of course, we represent the unknown in the problem. And in representing our unknown in the problem, we can make use of variables. It's either the variables x and y, or the variables a and b, or the variables x sub 1, x sub 2, or the variables y sub 1, y sub 2, okay? Depending on your preference. And after representing the unknown in our problem, the second step that we need to do is to formulate our objective function. And remember, there are only two objectives of the company. It's either to maximize the profit of the company or minimize the cost. Okay, in this case, since this is a minimization problem, then of course the objective function should be to minimize the cost. And aside from that, we need also to formulate our constraints, referring to the linear structural constraints and the non-negativity constraint by restating the information in mathematical form. And next, we need to convert the inequality structural constraints to equation by subtracting variable in a greater than or equal to and adding an artificial variable constraints. And after doing that, the next thing that we need to do is to enter the constraints coefficient in the initial tableau or table, and then we need to calculate C sub j minus Z sub j. And lastly, instead of looking for the most positive quantity in C sub j minus Z sub j row for the optimum column, look for the most negatively entry. And take note, whenever artificial variables are used, they can be dropped from the simplex table as soon as they have been eliminated from the basic feasible solution. So in order for us to be able to understand this one better on how to solve both maximization and minimization problems, we will have to provide examples of each. And so for that matter, that will be our next video to be made. So please stay tuned in order for you to get updated. All right, I think that's a good place to stop. If you have questions, please let me know on the comment section below. And if you like this video, please don't forget to subscribe and hit the bell button for the latest updates. Thank you.